Hello, everyone, and welcome to our makeup lecture for the second part of our statistics review. As I mentioned in the announcement, please try to have this lecture watched by the time of our exam review on Tuesday. Also, we're going to do handouts, even though it's a video lecture. So the handouts are available in the same module as this lecture. So if you haven't downloaded and/or printed those yet, uh, go ahead and do that, and then come back to this video. So the first thing we'll start with is the experimental design handout. So I'll give you a few minutes here. Obviously, you can just pause the video, take as long as you want, and then when you've finished with the handout, come back to the video, unpause it, and I'm going to go over the answers here in just a few seconds. So I'll give you a second to pause it. Okay, here's hoping you've done the experimental design handout. So the first question is to give an example of a good independent variable. And obviously there are lots of possible good answers here. If you're not sure about your answer, just ask about it in Tuesday's review session. But we've talked about some of these. For example, our music versus silence in studying experiment. So the IV there is music or silence, so ambient noise or ambient sound. Drug versus placebo, another very common independent variable. And we've also talked about IVs that include no drug at all, no pill at all. So you can compare placebo to no pill and drug to placebo. Also, things like compensation amount. So people might work harder if they have more incentive. One of the most famous psychology studies in all of psychological history involves a manipulation where you change how much people get paid to do a really boring task. And what's interesting about that one is that if it's really boring, everyone agrees that it's a boring task. Uh, but people think it's less boring if they're not paid very much. That seems a little bit odd. But the reason that is that if you're not paid very much, you have to rationalize why you just did that study and why you told someone else that it wasn't as boring as it really was. And so the way people rationalize that is they think, well, I must have enjoyed it because I didn't get paid very much. So it must have been an enjoyable task. So you can use compensation amount as an IV. Counterbalancing. This goes back to our unit on within participants designs, although it's also important for factorial designs if you have a repeated measure. So when you have a repeated measure, whether it's the entire experiment, totally repeated measures, or mixed in a factorial design, the main point there is to avoid those practice and fatigue effects. So when you have experience in one condition of a task, if it's exhausting, then you're not going to perform as well in the next part. Alternatively, if it's a tough test but it's manageable, you get more practice. And so if you always ran your repeated measures experiment with, for example, no music first and then music, uh, you might have a practice effect. So people would improve in the music condition, not because the music helped, but because they've taken the test before and they're used to it. Maybe they're less nervous. Alternatively, if the test is really tiring, they may do worse in the music condition. Not, again, because the music is harmful, but just because they're tired. So that's why you need to have half your group do music first and half your group do silence first. That's counterbalancing. One thing to remember here is that counterbalancing doesn't take care of carryover effects. So most famously in drug trials, if you're counterbalanced, you can be counterbalanced, but still have carryover effects because the manipulation in the first condition still has some effect in the second. And this is often the case with drug trials because you've changed the person biologically. It can also be true for cognitive experiments. If you give someone a study technique or memory technique, it's hard to avoid using it in that second trial. So counterbalancing can't take care of everything, but it does help with practice and fatigue effects. The difference between main effects and interactions, and this obviously bears on our unit for factorial designs. So a main effect is about what the effect is for an IV on a DV, just one independent variable. So if the DV changes a lot, as this one IV changes and does so consistently, then you've got a main effect. And that's in contrast to an interaction, where the level of the DV, the outcome, depends on a combination of independent variables. In other words, the effect of one independent variable depends on the level of the other independent variable. So that's what the interaction is. You can't just look at one IV and say what's going to happen to the DV. You have to know what all the IVs are doing, or multiple IVs are doing at least. So that's the difference there. Main effect, you just care about one IV. It has some impact on the DV. Interaction, it's not that simple. The DV is going to change depending on multiple IVs levels. Number 4, and this is why this handout is in this part of our course, is talking about the mode. We just went over descriptive statistics, and the mode, of course, is the most common value. So an example would be, what's your major? So that's nominal data, and as we know, the mode is most commonly used and is really the only appropriate measure for nominal data. So you can't put majors in an order that makes any sort of logical sense. You could alphabetize them, but there's no reason that majors increase in some sense. There's no zero major, so we don't have unit sizes, we don't have an absolute zero, and there's no obvious order in which to put majors, such that an increasing value, so to speak, would correspond to an increase in major. You can't say, oh, well, the major increased. And that's a good sign that you're using nominal data. So the mode would say what the most popular major is, and that's still useful. So that's where we would have a mode, is in nominal data. And then the last question was, what analysis would you use for a 3x4 design? So we have one independent variable with 3 levels, one independent variable with 4 levels, and we have a dependent variable that's ratio. And remember, we care somewhat about what kind of data, what kind of scale the DV is on. It could be interval, but most commonly ratio. Ratio data are the most common in psychology. There are some interval measures. But if we use our flowchart, which you got last session, you can see that this is a two-way ANOVA. There's only no alternative here. T-tests only work if you're comparing one independent variable with 2 levels. So once you're beyond 2 conditions, t-test isn't really on the table. So you could have one IV with 3 levels or more, and you'd use a one-way ANOVA. But here we have 2 independent variables, and as soon as you have 2 independent variables and ratio data, it has to be a two-way ANOVA. So that's just from your flowchart. We'll see later on in this lecture what that means, what a two-way ANOVA is. And of course, you've all had intro stats before, so you may have some familiarity with it, but we'll go over it again conceptually. Okay, so that brings us to inferential statistics. So last time we talked about descriptive statistics, things like central tendency, things like variability. And here with inferential statistics, what we're really trying to do is say something about the population, not just the sample that participated in our experiment. So with descriptive statistics, there's really no argument. You have the mean of your sample. There's no arguing about that. Inferential statistics, there's more uncertainty. But what you're trying to do is see if the IV, the independent variable, had an effect on your sample, but more importantly, whether your IV represents an important difference in the population. So whether it's an IV or even a subject variable, you're looking for differences, and not just differences in your sample, but you're trying to infer, trying to make an educated guess, whether there are real differences in the population as a function of this independent variable. So there's some concepts to go over first here. One is the null hypothesis, often denoted H sub 0, H naught. And this is always that the IV does nothing, that there is no difference between the groups, no matter how many groups there are. If you have 2 groups, an experimental and a control, for example, the null hypothesis is that there's no difference in our music versus silence study, that the number of items remembered in the music condition will be the same as the number of items remembered in the silence condition. So we're going to use inferential statistics to tell whether that's true or not, but that's the null hypothesis, that there is no difference. And that's in contrast to what's often called the research hypothesis, H1, and that is that there is a difference between the groups. So those are the two possible outcomes. There either is a difference or there isn't. So here, the research hypothesis, H1, is that the mean number of items in the music condition is not the same as in the silence condition. In other words, that unless there's a confound, that the IV had an effect. And it's important to remember that about confounds, that our data might turn out differently between the two groups. It might not necessarily be the IV that's doing it because of the possibility of confounds. That aside, what the research hypothesis suggests is that if it's true, there is a difference between these two groups, whatever the cause might be. Probably your IV, hopefully your IV, but it doesn't have to be. Now, standard approach is to use what's called a two-tailed hypothesis test. That is, you're testing whether one group is different than the other. It's non-directional. So for example, if we have some drug A, maybe that's the standard treatment for, it could be cancer, it could be any disease, but we have a new drug that we've developed, drug B, and we're curious if drug B does better. Now, of course, there are a couple of possibilities. One is that the drug B isn't different. One is that drug B is actually worse, that the mean survival, shown in this graph here, is less than it is for drug A, in which case we would stick with drug A for treatment. Another possibility, of course, is that drug B is better, that it extends life, that the months of survival are greater for drug B than for drug A. So you could have no difference, in other words, the null hypothesis. You could have a difference in one direction, and you could have a difference in the other direction. Drug B could be worse than A, it could be better than A. And so most research, you use this two-tailed hypothesis. You don't say up front whether drug B is better or worse. And you certainly don't constrain your hypothesis test in one direction or the other. If you actually knew with that much certainty, why bother running the study? So this is the usual way statistics are done, two-tailed hypothesis testing. You're just seeing if they're different. It could be better, it could be worse, but you'll tell either way. Now, your book mentions this one-tailed hypothesis testing, and I know Dr. Coolidge mentions this in psychological statistics. So here, a one-tailed test, you're effectively saying, my hypothesis is that drug B will, for example, be better. And so I only test for a difference in that one direction. What does this do? Well, it makes significance likelier. You're more likely to get a positive result in a one-tailed test because you're only testing in one direction. You're only testing one of the tails. And this is a little bit counterintuitive, but this is the way that one-tailed tests work. You're only testing in one direction. And so, for example, if you do a statistical test and you get a p-value of 0.08, two-tailed, testing in either direction, a one-tailed test, you have a p-value of 0.04. Now we know, and we're going to get into this in a second, that our criterion is 0.05. So two-tailed test, it's not significant. One-tailed test, it is. So this is an important distinction. And this has to do with the fact that we've got sort of an arbitrary cutoff for what's considered significant. Any cutoff would be arbitrary. We're going to get to that later. But this is why one-tailed hypothesis tests drive me a little crazy. And the thing here is that this is the only really domain in which what the researcher thinks determines whether it's a significant result or not. If you look at your stats flow chart, there is no sort of subjective component. There is no, well, do you think it should be a one-way ANOVA or a t-test? There are rules for it. There are rules for how you run the test. There are rules for how you calculate means. It's not up to your subjective judgment. But here, with this one-tailed test, it seems that it is. So if you have a hypothesis that's one-directional, that drug B will be better than drug A, you are allowed to run a one-tailed hypothesis test. I'm going to advise you to be really cautious about these, especially when you see one-tailed tests. Because again, they're not as common, but they are still widely used, and really more widely than they should be. And the reason is this, that you might have a non-significant effect if you run a two-tailed test, but again, a significant effect if it's one-tailed. So in our study with a two-tailed test, you'd say in our study we found no difference between the music and the silence groups, p equals 0.08. But in our study we found that music improved test performance, p less than 0.05, one-tailed, if I'm running a one-tailed test. So again, it makes the difference between a significant and a non-significant result. And so the reason this is widely misused is that if the researcher wants a significant result, they might run a one-tailed test, regardless of what they thought before. But again, even if they had a valid hypothesis before, and it was run in one direction, this is really the only area where a subjective judgment by the researcher gets to define effectively whether a result will be significant or not. So that's why I have big problems with that. And that's also why you should be wary anytime you see a one-tailed test, especially if it's p equals 0.01 or 0.03. Because, actually, never mind the 0.01. 0.03 is a good example. 0.03 is only significant if it's one-tailed. It'd be 0.06 if it were two-tailed. And so that's something to keep in mind. If you see a one-tailed test and it's significant, but only at p equals 0.04 or 0.03 or 0.025, bear in mind that that would not have been significant if you ran a standard two-tailed test. So that's why this drives me a little nuts. And this is why you should be careful, because it could be that the researcher ran the statistics the first time, two-tailed, the normal way, didn't get a significant result, then ran a one-tailed test, it became significant, and now that's what they're saying, is they had a hypothesis before. So be wary of one-tailed tests, avoid running them if you can. There are some special cases where I think they're valid, but they almost never come up in psychology. So just be aware of that. Your book doesn't really take a stance on one-tailed tests, but that's my stance, and that's also Dr. Coolidge's stance to a large degree. So be aware of that. Okay, so we have our inferential statistics. And one thing, again, is that we're trying to say something about the population. But we can make mistakes. Not computational mistakes, the way you could if you put in the wrong number for taking the mean. You can run your statistics absolutely correctly and still make a mistake. So for example, in the population at large, we have a couple of things that could happen. There could be no difference between two groups in the population. Again, it could be a subject variable like sex. It could be an independent variable that we've manipulated. And this is where we're basically saying, well, if we ran everybody in the world, or everybody in the population that we care about, there wouldn't be any difference. Now, that's not practical. We have to run a subsample. Or there could be a difference, H1. So we could have a difference between the groups or no difference between the groups. And that would be sort of our ground truth. If we ran it on everyone, either one outcome or the other will be the case. When we run our inferential statistics, we could find no difference, and that would confirm the null hypothesis, H0. Or we could find a difference and confirm the research hypothesis, H1. Now, obviously, if these match, that's great. So if there really is no difference in the population, and our statistics say there is no difference, that's a correct decision. Also, if there really is a difference in the population, and our statistics say there is one, that's also a correct decision. There's a match between what our stats say and what is actually true in the population. However, that doesn't have to happen. For example, a type 1 error is when our stats say there's a difference when there actually isn't one. That's called a type 1 error, and it goes in this box here in this table. So our stats say there's a difference, but if we measured everyone in the population, there really wouldn't be. And this can happen for a couple of reasons. One, you could have fluctuations in behavior in your sample. So maybe there were a couple of people in your groups that behaved oddly. And that can happen, especially if you don't have many individuals in your sample. Those odd behaviors by just a few individuals can make a difference. So that can bias your stats, and you could end up saying there's a difference when there really isn't one, just because of random fluctuations in behavior. Also, if you do your participant recruitment correctly, odds are you have equivalent groups uh, and groups that represent the population. But again, your recruitment's going to be subject to random factors. So maybe you accidentally, but through no fault of your own, got groups that really were different on some variable. And again, there are so many variables that characterize people that it's impossible to test them all and find that you had an equivalent control group on every dimension. So that's always going to be a danger. You could have people that really are representative of the population, but just happen to be having an off day and behave strangely. Or you could have groups that aren't equivalent on some variable, on some dimension. And even though you did your recruitment with the correct procedure, just by random chance, you got two different groups. And so again, you could say there's a difference, but really it's a difference in your groups, not a difference due to your IV. So you can end up with an accidental confound. So both of those can help your stats say there's a difference when there really isn't one. There's the opposite, a type 2 error. And here you said there's no difference when there actually is one. So H1 is true, but you didn't find a difference with your statistics. And there are reasons this can happen as well. One is sample size. So the more people you have in your study, the more statistical power you have. If you have really small groups of people, then even if there is a difference between the groups in the population, you might not see it because you're not collecting enough data to tell. Also, the precision of your measure matters. So if your measure is really noisy, if you're taking a survey and there are only two possible answers, well, that's not nearly as precise as a bunch of possible answers. So for example, I could ask, well, do you like this flavor of ice cream or not? That's a pretty imprecise measure. Now, if I said on a scale of -5 to +5, how much do you like this ice cream? I now have more precision. So how you take your measurement matters, and the number of people you measure matters. So those are both things that cause you to have a type 2 error, a small sample size or an imprecise measure. Okay, so that's how we can make mistakes. When we look at results for inferential statistics, there's a certain formatting and there's a certain meaning for those results. One concept here is statistical significance. Now, we've heard this term before, and this is usually summarized in a p-value. And p here is for probability. And the p-value is the chance, the odds, that if we find a difference, that difference was due to chance alone. So we know people are different. We know behavior can fluctuate. And so the amount of variability in the data and the number of samples we've taken both inform us as to the chance that any difference we see in the means is just random. And this is particularly true for small differences. So if you see a small difference in the mean, and you either didn't have many participants, or the behavior was really variable, odds are that's just due to random chance. So a p-value sums up those odds. And our criterion here is usually 0.05. Now what does that mean? It means that if the two means are different enough by our criterion, there is a less than 1 in 20, 0.05, chance that that difference is just due to random fluctuations. So if the p-value is greater than 0.05, that means that there's a greater than 1 in 20 chance that it's just due to random fluctuation, and we don't consider that to be significant. Now 0.05 is arbitrary. We could have picked any number, but across, and this isn't just in psychology, across all domains, 0.05 is the standard for significance. And so that makes an important difference because 0.04, we call it a significant result. It goes into one category. 0.06, which really isn't that different, it is non-significant, different category. And so we have to be a little wary. We have to look at the p-value itself. Now, sometimes people will report a trend if it's 0.06 to 0.1, so sort of in that middle ground. But always look at the p-value. Don't just depend on the label of significant or non-significant, because small differences in the p-value can change the label. Anyway, 0.05 is our criterion. So for example, if our p-value is 0.02, we would say it's significant, that the difference between the groups is not likely to be due to chance. If p equals 0.08, it is not significant. So odds are the difference is due to chance. And I say odds are, what I really mean by that is we're not sure enough about that difference to say that it's not due to chance. So again, we have to look at the p-value. 0.08 is pretty close to 0.05. So we would label it as not significant, but it's certainly different from 0.6, for example. So always look at the p-value. 0.05 is our standard, but the p-value can give us more information. Now, one important thing to keep in mind here is significance versus effect size. So significance, again, means that it's unlikely that the results are due to chance. Effect size is about how big that difference is. And this is important for a couple reasons. First, you might have a very significant difference between two groups, but the difference really isn't that meaningful or that big. For example, if I've got a weight loss program, I might see that a significant result, that everyone lost half a pound in the program, but everyone only lost a quarter of a pound otherwise in the control group. So if everyone followed that pattern, I would have a significant effect. However, a quarter of a pound difference between the two groups is not a very big difference. So you can have statistical significance, but not have a very big effect. This also comes up if you run large groups. So the more people we run, the more statistical power we have, and the more likely we are to find differences. But those differences numerically could be quite small. So that's an important distinction between significance, the likelihood of the difference being due to chance, and effect size, how big that difference really is compared to the baseline level of the measurement. So again, we have our criterion of 0.05. What if we change it? Let's say we change it to 0.025. Well, our chance of making a type 1 error just went down. We have a more stringent criterion. It's harder to get to 0.025 than 0.05. So we're less likely to find a significant result. Remember, type 1 errors are when we say there's a difference and there's really not. So 0.025, we're less likely to say there's a significant difference. So naturally, we're less likely to say there's a significant difference when there isn't one. Type 2 errors just went up. So if we're less likely to find significance, it now becomes more probable that we won't find a difference between our groups when there really is one. So there is no free lunch here. There is no optimal way to set the criterion where you can reduce both types of errors. You have to strike a balance. And so 0.05 strikes that balance. Again, it's sort of arbitrary, but that is what the community has settled on in terms of balancing type 1 and type 2 errors. If your criterion is too low, you'll never find a significant difference, even if there is one. If it's too high, you'll say there's a significant difference all the time when there really isn't. So we have to balance type 1 and type 2 errors. If we raise the criterion, we get the opposite problem. If it's 0.2, for example, now we only need less than a 20% chance to say there's a significant difference. So type 1 errors just went up, but type 2 errors just went down. So keep that in mind. That's why the criterion is 0.05, again, a little bit arbitrary, but it strikes that balance between type 1 and type 2 errors. So as for example, one common recent issue deals with mammography, mammograms. And medical institutions have recently started to say that frequent mammograms aren't all that recommended. And it's because of type 1 and type 2 errors. So first, mammograms only are helpful in a certain set of cancers, looking at breast cancer screening. And really fast-growing tumors, mammograms probably won't help because the tumor will grow too much between mammograms. Really slow-growing tumors, mammograms will catch them and they'll be treated, but those tumors wouldn't actually be harmful. And mammograms can't tell the difference between a fast-growing and harmful tumor and a benign, slow-growing one. So that's part of it. Part of it is also type 1 and type 2 errors. So mammograms can say that there's a tumor when there isn't. And mammograms can also say that there isn't a tumor when there is. So making mistakes of both kinds. And it turns out that those mistakes are common enough that having mammograms all the time is not helpful, and in fact can be harmful. First, things like radiation dosage. Also, because of the rate of false positives. Having a report that says that the person has cancer when they really don't causes psychological distress, certainly economic cost for treatment, and the physiological stress of treatment itself. So these aren't just esoteric statistical concepts. These things matter. And so what medical boards have done is institute rules or recommendations, really, for the frequency of mammograms and for the age at which one should start having them. And again, this is to balance type 1 and type 2 errors with the benefits of mammograms. Anyway, that's just an example that involves type 1 and type 2 errors and setting some sort of criterion. Here it's not statistical significance, it's how frequently and at what age should they be administered. But that's just one way in which this concept matters. Also, when we're running inferential statistics, there's a concept of multiple comparisons. And this is why we run ANOVAs versus t-tests. So if I have a 3x2 design, let's go back to our example of a new attention medication that we're testing in control populations and ADHD populations. And we either administer no pill, a placebo, or a new medication. So we have groups of people in each of these conditions. So we've got 6 conditions total. That's a 3x2 design. Multiply that out, you get 6. If we ran what we call pairwise comparisons, if we compared every single condition to every other condition, think of all the comparisons we have to run. We compare these groups to each other, 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 and so on. And that's not even all of the possible comparisons. But remember, we have a p-value criterion of 0.05. So what does that mean for us? Well, it means that any one test has a 1 in 20 chance, if it's significant, of being due to random fluctuations. That's fine if we're running one test. We can be fairly sure that it's due to the IV. However, if we start running a whole bunch of tests, now it becomes much more likely that a positive result, rejecting the null hypothesis, is just due to random fluctuation. Because we've run so many tests that odds are one of them is going to be positive at least. Just imagine if I had you flip a coin 4 times, the odds of coming up heads all 4 times are pretty low. If I have you flip a coin 100 times, the odds of you getting 4 heads in a row at some point in that sequence are pretty high. So that's why we can't just run pairwise comparisons and stick with our 0.05 criterion. So this is why we run an ANOVA, an analysis of variance. So t-tests only compare 2 groups at once. If you only have 2 groups, that's fine. If you only have 2 conditions. But if you have more than that, you run an ANOVA because you're not inflating the chances of getting a positive result just by doing a lot of comparisons. We don't need to go into the math or why this is, but an ANOVA effectively runs all the comparisons at once. It says, is there any difference between any of these conditions? And if the answer is yes, then you go in and you find which 2 groups are different, there could be more than 2 groups. But an ANOVA runs one test, what's called an omnibus test. You don't need to know that term. and test everything at once to see if there's any difference. And t-tests only compare two groups at once. So you have to worry about multiple comparisons if you run a bunch of t-tests, but not if you run an ANOVA. So that's why we have to worry about multiple comparisons, because then our p-value criterion becomes kind of meaningless. And that's why an ANOVA is an important test to run. Speaking of t-tests and ANOVAs, which one should you use? Well, we'll name what tests there are, and these are on your statistics flowchart. I'm not going to go into the chi-squared test or the Mann-Whitney U test. So those are sort of outside the scope of our course, and they're less commonly used anyway. You probably talked about them in psychological stats with Dr. Coolidge. But I'll go over a few of the tests on your flowchart and the ones that are most commonly used in psychology. So one is called the independent samples t-test. And this is where you have a between participants experiment. So you have two groups. One has what I'll call N1 participants, and the other has N2. So you have two groups. They could be the same size, but they don't have to be. But they're two groups with different people in them. So it's between participants. And we remember our between participants design. One of the most common ways to do this is just to have an experimental group and a control group. And again, those are two different groups of people. So you have one group of people and a different group of people in those two groups. And again, they could be the same number of individuals. They are in this picture, but they don't have to be. Now, when you are computing your statistics, you have what are called degrees of freedom. And this is a number that captures how much variability you can expect in your measurements. So here we can see that degrees of freedom for an independent samples t-test is N1 minus 1 plus N2 minus 1. Now, the point here is not to memorize that formula. There's no need to do that. But you can see that the degrees of freedom depends both on the size of the experimental group and on the size of the control group. If you increase the size of either one, you'll have more degrees of freedom. So when you see the result here, you'll see T paren, and then the number of degrees of freedom, close paren, equals, and then your T statistic that you computed. And then you'll have a p-value that indicates whether that result is significant or not. So in this case, it says T degrees of freedom 18 equals 5.59, p less than 0.001. So that would be a significant result. So we have our degrees of freedom, we have our T statistic, and we have our p-value. And again, those degrees of freedom depend on the size of the two groups. This is in contrast to a dependent samples t-test, where you have one group of size N1. So this is a within participants or possibly a matched participants design. Again, matched participants, we have a group of people in one group and a group of people in the other. And they're technically not the same people, but we've matched them on a bunch of variables. So we treat them as though they're the same people. Anyway, we have two conditions, and in a within participants, a repeated measures design, they experience condition A and condition B. Hopefully we counterbalance the order there. But you have the same participants in condition A and B in a within participants design, and you have the same group size because it's the same people. So a dependent samples t-test always has a group of size N1. And your degrees of freedom are N1 minus 1. Again, the point here is not to memorize the formula. It's to see that N1 is the size of the only group you have, and that's what determines your degrees of freedom. And this is really what makes the difference between the dependent and independent samples t-test in terms of power. Now, we've already seen that a within participants experiment has more statistical power. Why? Because you have one group of people. You don't have to worry about variability between two groups because due to subject factors, because your participants are the same people. Whatever characterizes them in one condition is the same thing that characterizes them in the other. So your degrees of freedom go down, and that gives you more statistical power. In the between participants design, the independent samples t-test, those two groups of people could be different in lots of ways, so you have more degrees of freedom. Anyway, the result looks very much the same in terms of formatting. T paren degrees of freedom equals 3.85, p less than 0.01. So again, a significant result. You have different degrees of freedom. You have a different t statistic. Uh, and this is not meant to be reflective of the same experiment run in a within participants way. This is a totally different study. But we see the same kind of formatting here. We have degrees of freedom, we have our t statistic, and we have our p-value. Okay, and that brings us to an analysis of variance, which I was just talking about a minute ago. An ANOVA is what you use when you have a factorial design, more than one IV. It's also what you use if you have just one IV, but more than one level. So for example, a no pill, placebo, and drug design. You have 3 levels for your IV, even though there's just one IV. You still use an ANOVA there because a t-test is only used for comparing 2 conditions or 2 groups. Now, there are different kinds of degrees of freedom within ANOVA. There's what we call between groups. So these are differences, or this is variability, between the conditions of your experiment. You also have within groups degrees of freedom. And this is variability due to differences between your participants. And you can expect both. So especially if your IV, if the levels of your IV change your measurement, your DV. But people are different. You're going to have fluctuations, differences between participants, even if they're in the same condition. And so an ANOVA compares these 2 kinds of variability. It compares variability due to levels of your IV, for example, and it compares variability within a condition that's just due to differences between your participants. And what an ANOVA does is say, is the difference that we see between 2 conditions really due to the level of the IV, or is it just due to variability between participants? So when you display the result of an ANOVA, you don't have a T anymore, you have an F, it's what's called an F test. And then you have your parentheses, but you have 2 different numbers in there instead of just 1. And those are your between groups and within groups degrees of freedom. The within groups will almost always be bigger because you almost always have more participants than you have conditions, for example. And you have those 2 numbers in parentheses. You have your F statistics. Here it's 0.23. So it's sort of like a t statistic. It's technically different in terms of how you calculate it. But the idea is that number is what you compare to a criterion for the F statistic. And then that gives you a p-value. Here we didn't find a significant difference. P is greater than 0.05. But that's how we break down that result. We have an F test, we have 2 different kinds of degrees of freedom, we have our F statistic, and we have our p-value. So it looks fairly similar to our t-test result, the 2 big differences being it's an F instead of a T, and then we have 2 kinds of degrees of freedom that we display separately. There are different kinds of ANOVAs. So there's a one-way. So you can have between participants, one-way ANOVA. In other words, you have, for example, your no pill, placebo, and drug trial groups. So you just have one independent variable with 3 levels: no pill, placebo, drug. But if you have 3 different groups of participants in those 3 conditions, that is a one-way ANOVA for between participants. And that matters because of the degrees of freedom you calculate. So again, between participants, I would have 3 different groups of people in each of my conditions, but I have 3 conditions, so I need to run an ANOVA, not a t-test. I could also have a repeated measures one-way ANOVA. I still have 3 levels for my IV, I still have 1 IV, but my group of participants experiences every level of the IV. Now, granted, drug trials are less likely to be using a repeated measures or within participants design, but especially for something like an attention med that wears off, it's possible. So they're both called one-way ANOVAs. The difference, just like the t-test, is how you calculate your degrees of freedom. We're not going to go into more details, but repeated measures statistically is more powerful because you have the same people in each condition, so you have less variability between participants. If you have a factorial design, if you have more than one independent variable, then you have a two-way ANOVA. If you have three IVs, then it's a three-way ANOVA, and so on. And here you can have between participants ANOVA, where every single condition is a different group. You can have repeated measures two-way ANOVA, where one group experiences all the conditions. Now, here in this design example, we can't do a repeated measures because you can't have people that are both in the control group and are in the ADHD group. That's a subject variable. But in theory, if it was a different experiment, it could still be 3 by 2, and you could have one group experience all conditions, just like our usual repeated measures design. You can also have a mixed factorial, and that's what I'm displaying here. You could have a control group, an ADHD group, and they experience each of the levels in our medicine IV. So no pill, placebo, and this new medicine we're testing. So again, ANOVAs avoid the multiple comparisons problem, but you can run an ANOVA for any of these designs. And whether it's a one-way or a two-way or a three-way or so on, depends on how many IVs you have. But as soon as you have more than one IV or more than two levels for a single IV, that's when you run an ANOVA. Okay, now that we know all that, let's do our statistics review handout. So I'll give you a second here to pause the video, do the handout, and then we'll come back and look at the answers. Okay, I assume you've unpaused the video at this point. So let's go over the handout. The first part of that handout is which measurement scale is being used. So there's some examples, and this is a review from way back in our early part of our course, looking at those scales of measurement, our variable lecture. So for example, reaction times. How long does it take you to push a button? That's ratio data. The minimum is 0. 0 means the absence of any time whatsoever. There's a unit size. So going from 0 to 1 second is the same size jump as from 1 to 2 seconds. So that's ratio data. T-shirt sizes. This is ordinal. It's tempting to say nominal because there's sizes like small, medium, large, and we're used to those verbal labels being nominal. But there's an order to be put in. So small, then medium, then large, then extra large. The increase in size isn't necessarily constant. So it can't be interval. But there's an order they can be put in even though they're names. So that's ordinal. Babies' weights. This is ratio again. A weight of 0 is the absence of any weight. And also the jump from 0 to 1 pound is the same size jump as 1 to 2. So we have a unit size. Types of food served. This is nominal. There's no logical order in which to put different types of food. And there is no 0. There's no concept of 0. These are just labels we put on things. So they're nominal. How much do you like a song? If it's on a -3 to +3 scale. And that's a common way to measure things like liking, qualitative data, subjective reports, things like surveys use these sort of -3 to +3 scales quite a bit. This is interval data. So you can go below 0, but you still have a unit size. -3 to -2 is the same size jump as +2 to +3. So we have a unit size, we don't have an absolute 0, so it's interval. The rankings of 25 football teams. This is ordinal. You're putting things in order. You have first place, second place, third place. So there is an order in which you can place them, but we don't know the difference in quality or difference in performance between any two teams. So the difference between the second place team and the third place team could be very small. The difference between the 7th place team and the 8th place team could be very big. We don't know. We can just put them in an order. IQ tests. And we talked about this before, again, earlier on in our course. This is interval data. It seems like ratio data because you would think that you can't get a score below 0 on an IQ test, but you can. In fact, the IQ tests are calibrated so that the average is 100, and then the better or worse you do, you just go away from 100. So you can actually get a negative IQ score. It is not likely, but it's possible. So these are interval data. Whether your social security number is odd or even, and this is one way of randomizing groups in an experiment. Social security numbers are assigned randomly. So you either have one that ends in an odd number or an even number. This is nominal. Any number is either odd or even. If you go down one, that number will be the opposite, but you can keep on going down. So there is no sort of zero level. It's not obvious whether odd numbers should be first or last. So this is just a category, and you can't put an order on it. So this is nominal. Okay, the matching. So type 1 errors, let's answer C, it's a false alarm. So you said there was a difference when there wasn't, if you measured the population. Type 2 error, that's D, a miss. There actually is a difference, but you said there wasn't one. So you missed that difference. Statistical significance, the answer is B. The idea that the difference we're measuring between our groups is not due to chance alone. So that is what defines a statistically significant result. And again, we usually use a criterion of 0.05 for our p-value. The null hypothesis. The answer here is A, that there is no difference between the groups. That is what we assume. That is our null hypothesis. And our statistics will tell us whether to accept or reject that hypothesis. Okay, and the last part of the handout was first, compute the mean, median, and mode for this set of numbers. The mean is 6.5, so if you add all those numbers up and divide by the number of values, that's the result you get. The median is 7, and 7 isn't in this list, but that's if you have an even number of values, then you pick the 2 middle values as opposed to just the 1, and then you average them. So 6 and 8 are the middle values. You average them, you get 7. So it's possible for the median to be a number that's not in the list. And then finally, the mode is 9. 9 shows up 3 times. It is the most common value, so that's the mode. The next question was about using 0.1 instead of 0.05. So this has to deal with our type 1 and type 2 errors. So a type 1 error is now more likely. We changed the criterion. It's now easier to reach significance. We only have a threshold of 0.1 as opposed to 0.05. So we're more likely to say there's a difference when there isn't. We're less likely to make a type 2 error. We're less likely to say that there isn't a difference when there is. So again, there's no free lunch. There's no way to reduce both types of errors just by changing a criterion. And then the next question was, you have an IV with 4 levels. You have a continuous dependent variable. And continuous is a term we haven't seen in a little while, but continuous means you can have values that are not whole numbers. And this is true for interval and ratio data. And you can use an ANOVA for those. So this is a one-way ANOVA. We don't have enough information to know whether it's between or within participants, repeated measures. So we can't say that. But we know it's a one-way ANOVA because we have 4 levels for our IV. And as soon as we have more than 2 conditions we're comparing, we use an ANOVA. Okay. And then finally, our last handout is that handout entitled Sample Study 1. So this is a little more practice. And so I'll give you a minute here to pause the video and do the handout, and then we'll go over the answer. Okay, I'll assume you've done the handout at this point. So this is the handout for sample study 1. And we have an experiment where you're getting either real protein or a placebo, and then either a small dose or a large dose of vitamin N, and then measuring bench press. So these are the data. These are just what are on the handout. So we have our two independent variables, protein supplement and vitamin N. We can compute our marginal means. For real protein versus placebo, we don't see a main effect. That's a very small difference. However, for the small dose versus large dose, we do see a difference. And it's a difference of 23, which is pretty big. So we can say there's no main effect of supplement, but there is a main effect of vitamin N, small dose versus large dose. So obviously the handout did not ask you for main effects, but if you did them, that's what they are. It does ask about interactions, and there is an interaction. Those slopes are pretty different. So we have, for the placebo group, small dose versus large dose of vitamin N makes almost no difference. However, the real protein group, there is a big difference. You have a small dose bench press of vitamin N of 210, and then that drops to 156 if you're on the large dose of vitamin N. So, in plain English, there is an interaction because the impact of vitamin N depends on whether you're on real protein or the placebo. If you're on the placebo, vitamin N doesn't really make much difference in terms of dosage. If you're on the real protein, however, going from a small dose to a large dose means a big drop in performance. So that's the interaction. Other questions on this handout. Is there a subject variable? No, there isn't. So people are assigned to receive small dose or large dose and real protein or placebo. These are both manipulated variables. So there is no subject variable. Is it completely repeated measures, independent groups, or a mixed factorial? So again, we look for our word or. They got either a small dose or a large dose of vitamin N. They received either a real protein supplement or a placebo. So that word or means you're only getting one level of each IV. So it is completely independent groups. Nobody's getting more than one condition of this experiment. Question 2. Could any of the following be a real statement of a significant effect? A could be a statement of a significant effect. B could not. So A, P is less than 0.01. B, P equals 0.56. That's not significant. C, also not significant. P greater than 0.05. So these are all properly formatted statistical test results, but the p-value tells us whether there's a significant effect or not. And then question 3 is a little bit different. It's not asking which of these is significant. It's saying which could represent the outcome of the study in question 1. Well, A and B are both t-tests. Those can only compare two groups. We have a factorial design. We have two independent variables. It has to be an ANOVA. And with that, it can only be C. C is an F-test. That means it's, for our purposes, it's an ANOVA. And we have the 2 degrees of freedom, 2 kinds of degrees of freedom. And it's not a significant result, but that could be the result, for example, testing the main effect of supplement. So it's not significant. Real protein versus placebo. And we have an ANOVA. We have a non-significant result. But again, because we have 2 independent variables, we have to use an ANOVA, which is an F-test. So for question number 3, it can only be C. Okay, so that will do it for the wrap-up on our statistics review. Next time, we'll do our exam review for exam 2, which is coming up on Thursday. So Tuesday the 19th, we'll do our exam review. Thursday the 21st, we will have our exam. And also, don't forget about those practice quizzes. Those are very helpful in assessing your knowledge of the subject material and in seeing the sort of questions you're likely to get on the exam. They're not the exact same questions, but they are the same sort of questions. So take a look at those as well, and I'll see you on Tuesday.